Welcome to lecture 4 of the wireless communication course, where we continue our study of the wireless channel. For today's lecture, we still continue in chapter 3 of the book, where I recommend that you read these highlighted sections. For some of them, you should not go into detail regarding the derivations. In today's lecture, we will learn the differences between delay spread, coherence time, Doppler spread, and coherence bandwidth, differences between narrowband and wideband communication, slow and fast fading. We'll also talk about how to compute the 2D autocorrelation function of wide sense stationary uncorrelated scattering processes. And we should be able to determine delay spread, coherence time, Doppler spread, and coherence bandwidth from this autocorrelation function, as well as its transforms. And then you should also be able to design communication systems that are either slow or fast fading, or narrowband or wideband. Now, this picture we've seen already a bunch of times. So we have a transmitter on the left, a receiver here on the right. If you send a very short pulse with a large bandwidth, you'll receive this wideband received signal. If you send a very long pulse that has a small bandwidth, then you will receive it like this. And so on the case on the right, all the paths in the channel are overlapping, and they give rise to then these fluctuations of the channel over time due to the coherent and incoherent addition of complex numbers. Now, to model how this channel behaves, so there are two aspects. One is the distribution, the other one is the autocorrelation. For the distribution, we've seen that the amplitude of the channel can be Rayleigh or Rissian. For the autocorrelation on the Rayleigh fading, we've seen the so-called Jake's model, where this autocorrelation function is related to the coherence time. This is also from last time. So once we decide on the carrier frequency, this tells us for a given environment, this channel impulse response, which depends on the delay tau and time t. We've seen the notion of delay spread, which is the time between the first and the last path in the impulse response. The inverse of that is the coherence bandwidth. When we study how quickly the channel changes, we've seen the coherence time, which tells us how long it takes for the channel to change, and its inverse is the Doppler spread. Once we choose a bandwidth over which to communicate, depending on the symbol duration, which is 1 over the bandwidth, if it's much larger than the delay spread, that means the communication system is narrowband, so you just have the addition of complex numbers. There's only a single resolved path in the channel. On the other hand, if the symbol duration is is smaller than the delay spread, we'll have wideband communication, leading to intersymbol interference. On the other hand, if the symbol duration is much smaller than the coherence time, we will have slow fading, where for many symbols the channel is constant. On the other hand, if this is not true, we'll have fast fading, where this channel can change symbol by symbol. So last time we focused exclusively on the narrowband case, and now today we move on to wideband communication. This figure shows these different cases. So on the top left, we should see the channel as a function of delay and time. In this case, the channel has multiple paths, so it's a wideband channel, but it doesn't change over time, so it's time invariant. On the bottom, the channel has only one resolved path, and this changes over time. So this is a narrowband fast fading channel. So again, recall, for this narrowband channel, the physical channel may have hundreds of paths, but since the bandwidth of communication is so small, we cannot see them at the receiver. And today, of course, we'll talk about this more general case with a channel that changes over time and over delay. This was the underlying general mathematical model, where we had the received signal as a function of the complex baseband signal, where we have a superposition of n paths. Each path has its own delay, its own amplitude, its own Doppler shift. And here again, we see the delay. Pulling out the carrier frequency, we obtain this received complex baseband signal, which we can write in the standard form as a convolution of the channel and the transmitted signal by introducing this time-varying channel impulse response. So now we have again the superposition of the n paths, but each path is characterized by a delta in the delay domain, an amplitude, and a phase. And this phase can vary very quickly with small differences in distance. When we have a narrowband fading channel, the channel only depends on t, not on tau. The tau is gone because there's all these paths add up together. So then this will become some n from 1 to n alpha n t e to the power j theta, sorry, phi n t, and then 1 delta t minus tau, where this is the same delay for all of the paths. Good for this channel, we've seen the distribution of the envelope of the channel, which could be really Orician. We've also seen the spectrum, which depended on the wide sense stationarity assumption. And again, today we talk about the wideband models. For this wideband case, we recall this slide from the first lecture, where we here have the convolution of a channel that has a delay but does not change with time, where we can use this Fourier relationship. When the channel is varying over time, we have a time varying convolution, so which is given by this expression. So C depends on tau and t. We can have a time varying frequency transform given by C of f and t. And as a special case, when the input signal is just a tone at a certain frequency, the output signal, if you plug this in, will be the same tone multiplied by this channel frequency response at that tone as a function of t. So this is just a complex number that changes over time, given this certain frequency f0. Here are some specific examples. So let's say that we have an environment with a delay spread of 10 microseconds. And here we have a delay spread of 100 microseconds. Given this delay spread, we can compute the frequency transform, which, let's see, is this one. So this is just computing the Fourier transform. Same here, if I compute the Fourier transform of this channel in blue, I obtain this red curve. So again, Fourier transform. So these notions of wideband and narrowband, you can also see in the frequency domain, which is shown in the bottom. If I have a signal like in here in green, which has a very small bandwidth, then over this bandwidth, the channel appears almost flat. Not exactly, but almost flat. And this means that the communication will be narrowband, because over the communication bandwidth, the channel does not change. On the other hand, if I have a wide bandwidth communication, the channel will change over the bandwidth of the communication. So here in blue is the bandwidth of a communication signal with a larger bandwidth, and within this band, the channel changes. Numerically, here, the delay spread is about 10 microseconds. That implies that the coherence band is about 100 kilohertz. So this means that if I have a communication signal with a bandwidth that is much less than 100 kilohertz, such as 10 kilohertz, like here, for this case, 10 kilohertz, which is the bandwidth, is much less than the coherence bandwidth, which is 100 kilohertz, which is equal to 1 over the delay spread. Right. Under this case, we have narrowband communication. For this second case, where the bandwidth is about 100 kilohertz, the bandwidth is on the order of the coherence bandwidth, so we'll have a wideband communication. The same happens on the right. So we have a delay spread of 100 microseconds, leading to a much smaller coherence bandwidth. So this means that in the frequency domain, the channel varies much more quickly, so that even with our 10 kilohertz communication system, the channel will change over this bandwidth. This is what we see here. So that means even with this 10 kilohertz bandwidth, this is approximately the coherence bandwidth. So this implies that we have a wideband communication. So the important thing is for the same bandwidth, in the left case, we have narrowband communication. And in the right case, we have wideband communication. This is because we communicate over a different channel. Okay, more repeating from last time. This is about autocorrelation functions for one-dimensional signals, where for wide sense stationarity, we need that the moments do not vary over time. So this could be a good candidate. The ones on the left and the middle are not satisfying this because the mean and variance change over time. This is the definition of the autocorrelation function. So it tells me to what extent the signal at a time t is correlated with the signal a little bit later. This does not depend on t when the signal is wide sense stationary. Now, before, so let me go back. This is the autocorrelation function of a one-dimensional signal. So here S of t is a scalar signal. You can also do the autocorrelation function for a two-dimensional signal. Oops, sorry. For a two-dimensional signal. So that, for instance, you have a signal here that has two parameters. And one of these parameters we call tau, the other one we call t. So I can actually try to make it a bit more general. So let's say you have S of two arguments, tau and t. In our case, tau will be delay and t will be time, but they could be general arguments. Then I could have the autocorrelation function of this process at tau plus delta tau, t plus delta t. No, that's not correct. Sorry. Autocorrelation function of this process at tau 1, tau 2, t1, t2. So it has four variables, and this is then defined as the expectation of S star tau 1, tau 2, no, tau 1, t1, S tau 2, t2. Okay, this is the general definition, and then we can apply this to our channel. So C of tau and t, and then we get this, this definition here. And here I just chosen t2 to be t1 plus delta t. Okay, so this is the general definition for autocorrelation function, which has four arguments. So what we will do now is we will reduce the complexity of this model, which will allow us to get rid of two of those arguments. And in that case, our autocorrelation function will just depend on tau and delta t. Okay, so we'll just have tau and delta t. And these assumptions are the following. First of all, when tau 1 is different from tau 2, we will say that the autocorrelation function of the four arguments is equal to 0. So two paths with different delay are always uncorrelated. And the motivation for that is that they bounce off different objects. They have nothing to do with each other. This already, excuse me, this already allows us to get rid of one of the four dimensions. And this is called the uncorrelated scattering assumption. The second assumption is the wide sense stationarity assumption, which tells us that if I have t and t plus delta t, the autocorrelation function is only a function of delta t, not on t. So whether I look at the correlation between, let's try to mark some points, at this time with respect to this time, or this time with respect to this time, this autocorrelation will be the same. They're equally correlated. And this allows us to get rid of most of the four arguments, so we'll only have tau and delta t remaining. So tau is the absolute delay, and delta t is the difference in time, or lag. Good, I think now our first 15 minutes are up, so I'll take a break.